My name is Stephan Zuchner. I'm a geneticist at the University of Miami. So we have heard all day the ambitions of synthetic DNA field, and this includes that we think there will be routine applications of this technology, and they will eventually leave the lab in the basic science and will be used in medicine quite a bit, but they will also be probably in agriculture, and certainly people think they could be very useful also to store information. And so they will be widespread, they will be out of the lab. And since it's DNA, it's going to be a long-lasting molecule. That's precisely why people suggest, for instance, to use it for information storage. As this becomes an industry, of course, this will be an international enterprise. There will be market forces that may be hard to control. And of course, there will be errors, there will be mistakes, there will be inadvertently or advertently release of products that may not be ready to be released. So we heard about the ethics and the concerns of the public. So what can we do proactively to sort of alleviate some of these anxieties? The idea is to sort of quite early in the development agree on sort of a watermark that should go along with all applications of synthetic DNA production. And this could be, the technology for this is there already today. This could use similar strategies than George Church had described in his paper on where he encoded his book. We could define a large space of such signatures, similar in a way to IP addresses in the internet. There could be a public trust that has these blocks of signatures, and you would be able to acquire such blocks, and they could be public blocks, or they could be actually private blocks, say for companies who want to have a certain degree of proprietary there. And the trick is really to keep the signatures small and then go to a database that knows about these signatures. And this is where the actual information is, the deep information, the annotation of what these signatures represent. So this is a brief flow. Whenever you have a synthetic element there, or it could also be a vector, a circular piece of DNA, or neochromosome, you would add a signature. And that signature could simply be nucleotides, but it could also have another layer which actually translates into a human readable format. And then similar, like you track with FedEx your package, you could go to a website and then you see all the detailed annotation that comes with this. So this may sound a little onerous to the field, but there could actually be very cool and useful applications for this. For instance, when you think about it, the future genome engineer may work more like a computer programmer. And in computer programming, good code is commented, right? And good code is saved in Git repositories, the different versions, and you have a sign of process in place. We have to probably think about similar things for DNA code when you create at large scale such products. And so when we have a wide space of such signatures, the future DNA engineer could just drop signatures on an artificial chromosome as he keeps working on this. This could be seamlessly integrated with software, say from Autodesk, and each of these signatures would actually help the company or the engineer to remember what was there. Why did I do this? Why did I do that? And so to do this, I think there's a unique opportunity in time because it's early in the game. We propose that we should build a pilot demonstration platform for that. We should test different signatures because they should be resistant to degradation and so on. And we should involve a community of interested scientists and probably do this with an industry partner early on to see if this is a viable idea. Thank you.